Dark matter and dark energy. These two things make up about 95% of everything that exists. Yet we can't see them or touch them. Sounds crazy, right? But don't worry. I'm going to explain it all in super simple words, like we're just chatting over coffee. I'll use easy examples, like spinning merry-go-rounds and blowing up balloons. We'll talk about how scientists figured out they're real, where those famous percentages come from, the standard model of the universe called Lambda-CDM, some problems it's having right now, and finally, a cool idea that maybe dark matter and dark energy aren't stuff at all. They could just be hidden bends in space-time itself. Let's jump in. What is dark matter? Imagine you're on a merry-go-round at the playground. The kids in the middle spin slowly, but the ones on the edge go really fast, right? That's because farther out, they need more speed to feel the same pull toward the center. Galaxies are kind of like giant merry-go-rounds made of billions of stars. Back in the 1930s, a scientist named Vera Rubin looked at how fast stars orbit around the center of galaxies. According to normal gravity, the rules we learned from Newton and Einstein, stars far from the center should orbit much slower than the ones close in, just like planets in our solar system. Mercury zips fast around the sun, but far away Neptune crawls. But nope. The stars on the outer edges of galaxies spin just as fast as the inner ones. The speed stays flat, like a record player. To explain this flat curve, there has to be way more gravity out there than we can see from stars and gas. Scientists call this invisible gravity source dark matter. It's like there's an invisible halo of extra mass around every galaxy holding everything together. Another cool example is the bullet cluster, two galaxy clusters that smashed into each other. When they collide, the normal hot gas, which we see in pink X-rays, gets slowed down by friction, like cars crashing. But the gravity, shown by blue lensing of background light, keeps going straight, separate from the gas. That invisible mass is dark matter. It doesn't bump into normal stuff much, it just pulls with gravity. In our solar system, almost all the mass is concentrated in the sun. It's in the center, and the planets are tiny compared to it. Gravity works like this. The closer a planet is to the sun, the stronger the pull. So it has to orbit faster to stay in balance, not fall in. Farther planets feel weaker gravity, so they orbit much slower. Examples: Mercury, super close, zooms around the sun in just 88 days. Earth takes 365 days. Neptune, way out there, takes 165 years. If you plot orbital speed versus distance, it drops off quickly, like a steep hill. Now, galaxies, the weird part. Galaxies like our Milky Way are huge spirals with billions of stars. If most of the visible mass, stars, gas, dust, was in the bright center, we would expect the same rule. Stars near the center orbit fast. Stars on the outer edges orbit much slower, just like planets. But when astronomers, like Vera Rubin in the 1970s, measured the speeds, they found something totally different. The orbital speed is roughly the same all the way out. Stars near the center and stars way out in the arms go around at about 200 to 250 kilometers per second. The curve is flat, not dropping. Why does this happen? Dark matter. To keep those outer stars moving so fast, without flying away, there has to be a lot more gravity out there than what we see from stars and gas alone. Scientists realize there must be a huge, invisible halo of extra mass surrounding the whole galaxy, dark matter. Dark matter doesn't shine or interact with light, but it has gravity. It's spread out in a big, fluffy sphere around the galaxy, not concentrated in the center. So inside most of the galaxy, you're always feeling gravity from a lot of mass, both visible and dark, no matter if you're near the center or far out. That's why the speed stays roughly constant. Okay, now dark energy. This one is about the whole universe expanding. Think of the universe like a balloon being blown up. Galaxies are dots on the balloon. They move apart as it inflates. In the 1920s, Edwin Hubble discovered the universe is expanding. In the 1990s, scientists looked at really far-away exploding stars called supernovae to measure how fast it's expanding. They expected the expansion to be slowing down because gravity from all the stuff should pull everything back. Like throwing a ball up, it slows down. But surprise, the expansion is speeding up. Something is pushing everything apart faster and faster. We call that mysterious push dark energy. It's like an anti-gravity that gets stronger as the universe gets bigger. So, dark matter holds galaxies together. Dark energy pushes the universe apart. Now, how do we know the percentages? About 5% normal stuff, 27% dark matter, 68% dark energy. These numbers come from many different measurements that all agree amazingly well. The biggest one is the cosmic microwave background, or CMB, the leftover heat from the Big Bang, like the glow in an oven after you turn it off. The CMB is a snapshot of the universe when it was only 380,000 years old. It's super uniform, but has tiny hot and cold spots. The size and pattern of those ripples depend on how much normal matter, dark matter, and dark energy there was back then. The Planck satellite measured it super precisely and got roughly 5% normal atoms, 27% dark matter, and 68% dark energy. Other evidence like galaxy clustering, gravitational lensing, and supernova distances all match these numbers. It's like a puzzle where all pieces fit perfectly. This whole picture is called the Lambda-CDM model. CDM means cold dark matter that moves slowly, and lambda is Einstein's cosmological constant, which is the simplest way to explain dark energy, like a built-in push in empty space. Lambda-CDM is the standard model of cosmology. It predicts everything from the Big Bang to today incredibly well. It's like the periodic table for the universe. But it's not perfect. There are some cracks called tensions. The biggest one is the Hubble tension. The Hubble constant, h0, is how fast the universe is expanding right now. From the CMB, early universe, plus Lambda-CDM, we get about 67 to 68 kilometers per second per megaparsec. But when we measure it directly in the nearby universe, with supernovae, Cepheid stars, etc., we get around 73 to 74 kilometers per second per megaparsec. That's a difference of more than 5 sigma, way too big to be a fluke. It's like two teams measuring the same room and getting different lengths. Another tension is the S8 tension. S8 measures how clumpy matter is on large scales. CMB says it should be higher, but galaxy surveys see less clumping. And just this year, 2025, the DESI experiment looking at baryon acoustic oscillations, sound waves in the early universe, hinted that dark energy might not be perfectly constant. It could be changing a tiny bit over time. These tensions mean something might be missing in Lambda-CDM. Maybe new physics. One exciting idea is that dark matter and dark energy aren't new kinds of particles or energy at all. They might just be the way space-time itself curves in ways we haven't fully understood yet. Remember Einstein's general relativity? Gravity isn't a force. It's the curving of space-time by mass and energy. Maybe on huge scales or very low densities, gravity works a little differently. Stronger in galaxies, mimicking dark matter, and repulsive over cosmic distances, mimicking dark energy. This is called modified gravity. Theories like MOND for galaxies or far gravity change Einstein's equations a bit to produce these effects without extra stuff. Some even include ideas from quantum physics, like entanglement creating extra curvature or entropy, disorder, driving the expansion. If true, the dark parts are just hidden geometry, extra bends and twists in the fabric of space-time we haven't mapped yet. We don't know if this is right, but upcoming telescopes like Euclid, Rubin Observatory, and more DESI data will test it. If Lambda-CDM keeps having problems and modified gravity fits better, we might be on the verge of a big revolution. So that's the story of dark matter and dark energy. Mysterious, but backed by tons of evidence, powering our best model. Yet maybe pointing to something deeper about space-time itself. What do you think? Is it invisible stuff or bent geometry? Drop a comment below, smash that like button if you learned something, and subscribe for more space mysteries explained simply. Until the next time, take care.